Thank you, sir.
Okay, good morning. So today is the second day of our conference, and let us welcome our invited speaker, Professor Samarjit Chakraborty. He is a very good and old friend of mine, and he is internationally well known in the area of embedded systems and automotive systems. But nevertheless, so let me introduce him formally. So Professor Chakraborty is currently holds a distinguished professorship at the Department of Computer Science at the University of North Carolina at Chapel Hill. Now, prior to that, he was a professor of electrical engineering at the Technical University of Munich for more than a decade, where he held the chair of real-time computing systems. He received the PhD degree from ETH Zurich. Now, his research interest includes hardware-software co-design for embedded systems and autonomous vehicles. He is on the editorial board of many top-rated IEEE transactions and ICM transactions, and he received numerous awards, including several Best Paper Awards, Humboldt Professorship. He is a fellow of the IEEE and a consultant to many corporates like GM, Intel, Google, BMW, Siemens, and Bosch. Professor Chakrabarty.
Thank you very much. Can you all hear me? Okay. Yes, so it is a great honor to be introduced by Bhargavda, and I also would like to start by thanking the organizers for inviting me to give a talk yet once again. Some of you might have attended my talk last year in January when I was able to go there in person. Unfortunately, because the classes here at UNC Chapel Hill started today, I could not attend this conference in person. So I would like to start before I go into the topic of today's talk. I would like to start by sharing some development since I gave the other talk last year. So if some of you attended that talk, you might recall that it was on the problem of neighbor discovery. That was a more algorithmic kind of talk compared to what I'm going to talk about today. Now, I kind of see academics like us, and by us, I don't mean just me, but all of us here are, in some sense, have a lot of similarity with rock stars. Why do I say that? Because, you see rock stars kind of come up with this, one piece of music and then they go on a world tour and kind of play that in many different concerts. So similarly, people like us, we, do one piece of work and then we go around, giving lots of different talks at different places on that work. But I would like to tell you that last year, when I gave that talk on neighbor discovery, I had not given that talk anywhere before. We had a paper at SIGCOM a couple of years ago. Then we had several journal papers, but I didn't have to go and give that talk in a conference. My student had given the talk at SIGCOM, and this was the first time I gave that talk. And of course, therefore, it was not very easy because just before coming to your conference, I was in Bangalore attending a different conference. So I was frantically sitting, for several days trying to prepare my slides. But unfortunately, I still couldn't finish them. So I came to Calcutta on the day before, late in the evening. It was beyond 10. And I was still sitting in my hotel room and working till like 4 in the morning trying to complete my slides. And finally, I managed and I gave the talk. But since then, I gave that talk in January, and then in March, I had submitted a proposal. It is not quite a regular proposal, but it was, a proposal actually for an award. In Germany, there is something called the Dieter Schwartz Foundation. And the Dieter Schwartz Foundation funds something called the Dieter Schwartz Courageous Research Grant. So based on the work that I did, and then I gave the talk, and it was, I thought pretty well received by all of you. So I felt very enthused by all that. And then I wrote a proposal trying to address many different generalizations of what I had spoken about. And a couple of months later, I was informed that, that proposal got funded. So I essentially got an award from the Dieter Schwartz Foundation. And the reason I tell you all of this is because this means that I'm going to keep on working on that problem on which I gave the talk last year. I'll keep on working on that problem at least for the next, 3 years. The duration of this award is for 3 years. And hopefully we will solve many other problems which are generalizations of what I spoke about last year. But today's talk is on a different topic, and we have been working more actively on this topic. And today is not going to be the first time I'll give this talk. So I have given not exactly this talk, but similar talks at other places. So preparing today's slides was much easier. And I would also like to say that, I think I have been a little unlucky with this conference because last year when I gave the talk, as I said, I was in Bangalore attending some other conferences, so I could only come and attend the last day of your conference, and the banquet and so on was already over. And I always very much like attending conferences in India because the food is so great, right? There are no conferences these days, not even in Europe, the conferences serve the kind of food one gets to eat in India, and especially given that your conference is happening in Calcutta, it's even better. And I still remember that the one lunch I had, the fish fry tasted excellent. And unfortunately, I forgot to ask Bhandarida what kind of menu you are going to have in today, this year's banquet, but I will unfortunately miss it. But I'm hoping that you will organize this conference again, and if you invite me again and it is at a opportune time, then I will come and certainly again attend that in person, and maybe this time I will be able to also attend the banquet. So with that, I will start. I will go into the topic of today's talk. It is about perfectly imperfect autonomy and machine learning. Now, I will first start with an example. So I'll shift and show you something else. And so this is a setup. I hope you are able to see this. So this is a setup where you see that here there is a levitating ball, right? It's a metallic levitating ball. And the goal is that this ball should be floating in the air. It should be levitating in the air. And of course, like, normally under gravity, it will fall down. But, on top of this, there is a magnet, and it is an electromagnet. And by adjusting the amount of current that flows through the coils, we are able to adjust the magnetic field. And by appropriately adjusting the magnetic field, this ball can stay levitating in the air. So, of course, if the magnetic field is not sufficiently strong, then the ball is going to fall down. And if the magnetic field is too strong, then the ball is going to get sucked in. And therefore, it is extremely important that the current is appropriately controlled. Now, of course, you can immediately see that the way the current has to be controlled also depends on the position, depends on the exact position of this levitating ball. If it is, close to this magnetic, if this close to the surface of this, magnet, then of course the amount of force should be reduced. If it is further away, then the amount of force should be increased. So therefore, the adjustment in the current depends on the exact location of this levitating ball. And the way we detect this position is using this camera. So this camera essentially detects the position. That position estimation is then fed into some feedback controller, and that controller then adjusts the magnetic field. And as a result, this ball has to keep on floating in the air. Now, the reason I show you this is because this is a surrogate for lots of different applications that are of interest for the purpose of the talk that I'm going to give now. So for example, you can see that this is a surrogate for lots of autonomous systems like autonomous vehicles, where your car might using things like such cameras or lidars or radars estimate the position of other vehicles in the surroundings or the vehicle in the front, and then adjust its acceleration speed, etc., in order to, for example, not go and collide. So in order to maintain some or satisfy some sort of safety property, there is the vision processing. Today, most of that is done using a neural network, and then there is some feedback control, and then there is a actuation that goes on. So let's look at this video and see what happens. So here you see that we will bring this ball, and it is a inherently unstable system, so it has to be appropriately positioned. And there you go. And you see that it is floating in the air. And this camera is essentially tracking the position. And this is a gigabit Ethernet camera. So it is capturing a lot of data at very high speed, and this data has to be immediately processed, and then appropriate control action has to be taken. Now here you see that this levitating ball, although it's supposed to remain exactly still, but it is not. It is somehow sort of vibrating in the air. And there are, of course, many reasons for that. The reasons could be there are external disturbances, like there are air movements. Of course, the model that we have, that model based on which the control action is being taken, the model should reflect this physical system exactly, but in reality it doesn't. There is a little bit of deviation and so on. Okay, so with that setup, I will go into the main topic of the talk. So let me share my slides once again and go to what I'm trying to tell you here. So if you look at sort of emerging autonomous systems, you will see that these systems are essentially combinations of lots of different things. I mean, there is complex control, there is, of course, machine learning, there are lots of different sensors. The sensor data can be noisy, so there are lots of filtering algorithms. Then, such systems have to be secure. There are lots of different schedulers that have to ensure that everything happens within the right time. So there is some timeliness requirement, and many of these components you already saw in the example that I showed you just now. There was, of course, control. The position estimation here, it was relatively simple image processing, but in other cases that could be a lot more complex. So there are machine learning components. The camera data that is being captured might have to be filtered. In other cases, if there is a LiDAR and so on, then that filtering requirement is even higher. We didn't have security, but in many systems there could be security. Now, the point that I would like to drive home is that in the traditional design approach, each of these component today is designed in isolation. So if you go to a big automotive company or even a big engineering company, let's say like, Siemens or Bosch or BMW or General Motors, there are all these different units that they have. And there is one sort of division that is responsible for control. There is another division which is probably responsible for the architecture of the system. There is another division responsible for machine learning and so on. And they pretty much work independently. And whatever they are trying to design, like if they are trying to design some machine learning components, the goal is, of course, to design that component to perfection, right? And we see a lot of that today. There is, increasing volumes of research trying to design machine learning algorithms that have better and better inference quality. Now, once all of these components are designed, then the final goal is to put these components together, and then the system should work. Now, of course, we know, everybody knows that although the goal is to design these components to perfection, in reality, none of these components are perfect, right? The machine learning components actually do make some inference errors, despite, how hard you might try to make them perfect. The scheduling algorithms will occasionally make some, errors, or will be a little imperfect, and deadlines will sometimes be missed. But the design philosophy is that the goal is to make these components perfect, and we assume that whatever imperfection is there, that imperfection is small enough that it could be neglected. Now, in reality, that usually is the case, that these imperfections are small enough and it is, neglected. But as systems become more complex, then the interactions between these imperfections of different components become very difficult to analyze or predict, and therefore, what actually happens in practice becomes, a lot more difficult to envision. And more importantly, as systems are becoming more complex, trying to design all of these components to perfection is trying out to be extremely expensive, right? And especially in the context of machine learning, we already see this today, that, although we are being able to do better and better, but the amount of compute resources that are needed, the amount of energy resources that are needed, is almost becoming unsustainable. So, therefore, the question is, do we really need this level of perfection? And what I will try to argue today is that we, in general, do not need the level of perfection that we commonly try to pursue. So, for example, the machine learning components do not need to always make perfect inference. And even without making those perfect inferences, we can design systems that are perfectly acceptable and perfectly fine. So the goal really is that rather than making the assumption that the imperfection is negligible and our goal is to design the perfect component, we would instead, and this is what I propose, that we instead try to design systems where we accept the imperfection from the very beginning. So, in some sense, we want to design an imperfect system. So, the goal of having the component being imperfect is already baked into the design. Okay, so our goal is to really understand how much the system can be imperfect, and we aim to design that imperfect system. We do not aim to design a perfect system. So how does, this work? This, of course, sounds a little unusual, but I will show you that, this design philosophy can actually result in systems that are not only perfectly acceptable, but also such a design philosophy is going to be a lot more sustainable in the future, and we can we can we can provide safety guarantees for this kind of design. So how does this work? Now, the first thing is that we will say that, let's say we are trying to design an autonomous vehicle, and this vehicle has all these different components that I spoke about. All that matters to us is that this vehicle satisfies its high level goals. Now, what can these high level goals be? They could be that, for example, the vehicle doesn't go and collide with something. Let's say in the case of this figure, the goal is lane following. So, this vehicle has to be in the middle of the lane and, should not cross over to the pedestrian zone. Now, while meeting that goal, the goal that really matters, that is, the vehicle is in the middle of the lane, for the different components, like the machine learning component that is inside it, whether it is making the perfect inference or it is making occasionally some erroneous inferences, we do not care. Similarly, for the scheduler, whether deadlines are being occasionally missed or not, we do not care, as long as the high level property that matters to us, that is, the vehicle is in the center of the lane, as long as that property is satisfied, we are happy, right? So now the question is that in order to proceed with this idea, the first thing we would like to do is we would like to define a concept or a notion of system level safety. So there could be many different notions, and I will talk a little bit more on this at the end. But let's for the purpose of today's talk, we will consider one very intuitive notion of safety. And that intuitive notion of safety is that let's assume there is an ideal behavior. So in this case, the ideal behavior is the vehicle is exactly in the center of the lane. So as long as the vehicle deviates within some threshold from that ideal behavior, we say that the system is safe. So in our case, that ideal behavior, as I said, could be that the vehicle is always exactly in the center of the lane, but then we kind of define some sort of a safety pipe around that ideal behavior, and as long as the vehicle stays within that safety pipe, we say that the behavior is safe. So our safety pipe could be the width of the lane. So of course, ideally the vehicle should be exactly in the center, but as long as it is within the lane, it can deviate a little bit from the center. Usually we are perfectly fine. So if we admit this notion of safety, which is a slightly relaxed notion of safety, so because we are defining a pipe around the ideal behavior, then the question is how much imperfectness can the different components of the system admit, or how much imperfectness can be allowed for the different components of the system. So let's try to understand this a little bit more formally. So let's say that, now I have a system. So for any such autonomous system, there is a ideal behavior. So let's say the system has a state space. In this example that we see, let's say the state space is two-dimensional. There is the two components are x1 and x2, and the system then evolves over time. So the vertical axis is the time. And now you see that the behavior of the system can be defined as some trajectory in this state space. So here, let's assume that we have a black trajectory. You can see that at the center, there is a black trajectory. So this black trajectory is the ideal behavior of the system. That is, the car is always exactly in the center of the lane. And then we define a safety pipe around this ideal trajectory. And then as long as a trajectory is within the safety pipe, we say that the behavior is safe. This is an admissible behavior. So all the green trajectories that we see, these are all acceptable behaviors of the system. But if the trajectory goes out of the safety pipe, like the red line, this is an unsafe behavior, right? So we cannot admit this, but anything that stays within the pipe can be allowed. So now the question is that if I now have this imperfect cyber physical system or imperfect autonomous system, which is the safety property plus the allowed margin, then the question is how much can we relax each of these other components of the system, right? Let's say how much timing violations can we now tolerate? How much modeling uncertainty can we tolerate? How much sensing errors can we tolerate? How much ML inference errors can we tolerate? Now, if we can tolerate significant amount of errors in these components, it means that these components can now be designed in a much more cost-efficient fashion. They might require less compute resources, etc. And the overall design is a lot more cost-effective, but we are still ensuring that the system works fine. It is safe. And in fact, this is even a better design approach because in the traditional approach, where we are admitting only one behavior, namely the black line, and we know that that behavior is not achievable, we are essentially just ignoring the deviations from this black line. And we saw that in the video that I showed you, that levitating ball was not standing still. It was kind of, vibrating around the desired location. But we did not explicitly take that into account. But if we would have taken that into account and designed all the components appropriately, the question is, could we have designed a more cost-effective system? So I will show you that starting from this system level safety description, deriving allowed component behaviors, this is actually a non-trivial problem, but it can be solved. And if we can solve this, then we can design systems much more cost effectively. So the research questions that come up are several, right? So one of the obvious research questions is, how do we specify this system safety? I gave you a very intuitive notion, but even here you might ask, okay, how much should be the diameter of the safety pipe? The second question, of course, is how do we translate such a system safety specification into component behaviors, or given different component behaviors, can you ensure that if these components are put together, the overall system is safe? Given component behaviors, how do you coordinate them so that you can meet system safety? So for example, if there are bigger timing variances, or there are higher machine um, ML inference errors, then you might be able to compensate for that by appropriately designing a more aggressive controller. Or how does the cost efficiency change as system safety is relaxed, right? If you go to a engineer and say that, well, if you can allow a slightly bigger safety pipe, then we can reduce your cost by 60%, and they might be perfectly happy in doing that. So the question is, what is this trade-off? So all of these are relevant questions in this design paradigm, and answering them are it's not very trivial to answer them, but if we can, then this can be a very useful approach. So before we progress, I would like to, set the stage a little bit. So many of these autonomous systems that we are interested in, essentially, they would implement some sort of feedback controller, and we don't expect any deep control theory knowledge, but the whole idea is that I have a physical system like an autonomous car. So I have a model of this physical system. So here you see there are some differential equations specifying the model of the system, and what the overall autonomous behavior is going to be is that we have some sensors. They sense the state of the system, like let's say the position of the vehicle with respect to the other vehicles in the surroundings. And then based on the sense state, we compute a control action. This is the controller. And so that control action could be, how much should the vehicle speed up, or, how much should the steering angle change. And then on the basis of that, computed control action, we actuate. So we actually influence the system. And this keeps on, happening in an infinite loop. And the goal of designing the controller would be that I want to impose a certain desired behavior on the system. And that desired behavior, as I said, could be that I want to keep the vehicle in the middle of the lane, or the robot arm has to go and grasp something, or it could be pretty much anything. Okay, so what I will do is, that's essentially the high level message of my talk, and I didn't show you how this can be done, or whether this approach is at all feasible or not. So what I'm going to do is, for the rest of this talk, like the approximately half an hour that I have, I'll give you three examples. I'll give you three examples to show or try to convince you that what I'm talking about is actually feasible. Okay. So the first example I have is, if you design, this kind of systems, the typical design philosophy is that somehow safety is equated with meeting deadlines, right? If I have a safety critical system, then the critical tasks, or like the control tasks, should not miss deadlines. And I work quite a bit in real-time systems, and this entire real-time systems community is bent on trying to ensure that for safety critical systems, the tasks do not miss deadlines. So there are either schedulability analysis techniques, and you analyze the system to ensure that under no circumstances deadlines are missed, or there are scheduling algorithms using which you enforce certain behaviors such that deadlines are not missed. But now the question we are trying to ask is that, what if we allow deadlines to be missed? Given such a system level safety property, can we try to figure out how many deadlines can be missed? And if we can figure out what kind of missing behavior is allowed while keeping the system safe, then can we somehow exploit this idea to design a better or a more cost-effective system? So again, the whole idea is that I have my nominal behavior, which is this black line, and then I have a safety pipe around it, and then any behavior that stays within the safety pipe is acceptable. So given that, the question I'm trying to ask is, if there would be a control task, then what kind of deadline misses? If there is a deadline miss, then it means that, I am not actuating the system appropriately. Now, of course, then the behavior of the system is going to deteriorate. So therefore, it's not going to remain the black line. So let's say the black line is the behavior when all deadlines are met. And if some deadlines are missed, then the system behavior will change. So you'll get perhaps a green line. And the question we are trying to ask is what kind of deadline miss patterns will keep the system within this safety pipe? So we don't want a deadline miss pattern that drives the system out of the safety pipe, but we are trying to ask what are all possible deadline miss patterns that keep the system within the pipe. So how can we solve this problem? This is actually a non-trivial problem to solve. Now, in order to solve the problem, the first thing we will do is we will try to settle on some description of deadline miss patterns. And the description, there could be many different descriptions, but the one we will choose for today is we will specify deadline miss patterns using a tuple. The tuple is M and K. And the meaning of M and K is that if I look at a sequence of periods, then of, let's say, length K, then MK will denote all possible deadline hit and miss patterns where within every window of length K, there are at least M deadlines that are hit. So at least M deadlines are satisfied. And then K minus M deadlines can be missed. So let me give you an example. So let's say that, my tuple is 3, 5. And now I look at a concrete pattern of deadline hits and misses. So 1 denotes that in this period, the deadline was met. Then in the second period, the task missed the deadline. Then again, the task met the deadline. Then again met the deadline. Then missed the deadline. So if this is my concrete pattern, this is one pattern of deadline hits and misses. So I put the window here and you see that within this window of length 5, there are 3 hits. So this is fine. So then I move it along and here again, I see 3 hits and 2 misses. This is also fine. Here it is also fine, 3 hits and 2 misses. But here it is not, right? In this position of the window, you see that there are only 2 hits. So therefore, this concrete deadline hit miss pattern does not belong to 3, 5. So you can see from this discussion that 3, 5 is essentially denoting a language. So it is denoting a set of binary strings where each binary string is a concrete deadline hit miss pattern. There are certain binary strings that belong to this language 3, 5. And there are other patterns like this one, it does not belong to this language. So if I would have turned this 0 to a 1, then this string would have belonged. But if this remains a 0, then this string does not belong. So this is the description of languages that we will use. And now the question is that given a particular language MK, so let's say given a language 3, 5 or, let's say 5, 7 or, 3, 10, we are trying to ask, is this language of deadline hit miss pattern safe? That means that any concrete deadline hit miss pattern that belongs to this language, will it keep my system trajectory within the safety pipe? Or in other words, I'm trying to ask, what are languages of deadline hit miss patterns of this form, of the form MK, such that the behavior of the system is within the pipe? Now, how do we answer this question? Now, what we will do is, for let's say a given control application, we will guess a regular language. So let's say we guess 3, 5, okay? And now I want to check whether 3, 5 is safe or not. So what we will do is we will use what is called reachability analysis. So in other words, in some sense, I'm sort of being a little inaccurate here to simplify things. So what I will do is I will take, let's say, all possible strings that belong to this language 3, 5. And what I will do is I will start with an initial state and explore how the system evolves and check whether the system stays within the safety pipe or not. This is what is called reachability analysis. I am essentially trying to identify all the points in the state space that are reachable. And if all the reachable points are within the safety pipe, then the system is safe. Now, of course, this is not feasible because the given a language like 3.5, the number of possible strings that belong to this language can be very large. And therefore, I would kind of, this would become computationally intractable. So we would use something like an approximate reachability analysis. So what I would do is I will start at an initial state. If it is a hit, the system goes here. If it is a miss, it goes here. Then from here, there are two possibilities. And after some time, I have all of these possibilities, but rather than keeping track of these possibilities, I will essentially approximate this whole thing with a convex set. And then from there on, I will see how does this convex set evolve. Now you see that this is a safe approximation because by approximating all of these points by a convex set, I am admitting behaviors or points in the state space that are actually not reachable, but every point in the state space that is reachable is actually taken into account. So by doing this approximate, excuse me, by doing this approximation, I can more effectively compute whether, let's say 3 comma 5 is safe or not. So now what we can do is you will also see that a language of the form that I defined, and this was intentional, this something like 3, 5 or MK in general is actually a regular language. What is the meaning of that? It means that corresponding to this language, we can design trivially a finite automata such that any string that belongs to this language will be accepted by the finite automata and any string that does not belong to the language will be rejected by the finite automata. Now, once I have this safe timing behavior, I will show you that using pure automata theoretic techniques, we can synthesize schedules that are very cost effective in designing these kinds of systems. So, in order to understand this, let me give you an example here. So, what we assume is that, let's say I have a system and I have 5 different tasks, right? These tasks are T1 to T5, and my time is slotted. So, I have this time slots, and in each time slot, out of the 5, I can schedule at most 2 tasks. Okay, so in the first slot, I schedule task T1 and T3. In the second slot, I schedule T1 and T2. In the third, I schedule T3 and T4, etc. Now, the other tasks that I am unable, that I did not schedule, like here, it would be T2, T4, and T5, they will miss their deadlines in the first period. In the second slot, I am not scheduling T3, T4, T5, so they will miss their deadlines. Now, the question, and I might have a constraint like that because I have a resource constraint processor. The processor at any point, any time slot can run only 2 tasks, but not, all the 5. And the question I'm asking now is it possible, given all these, 5 tasks and given their corresponding safety pipes, they are all different. Can you hear me? There was suddenly some echo. Okay, so the question I'm trying to ask here is, given this, safety specifications of these 5 tasks, is it possible to schedule them in this manner such that in every slot I schedule no more than 2 tasks, such that all of them are safe? So how do we do that? Now, the first step, as I said, we have the languages corresponding to the safe languages corresponding to each of these tasks. So because these languages are regular, I have a finite automata. So this is the finite automata corresponding to task 1, task 2, task 3, 4, 5. And what I will do is I will create a product, right? I will not go into what is the meaning of product construction for finite automata, but I will construct a product. So which means that in the product automata, each state is essentially a 5 tuple, right? The state comes from, each one of the states from each one of this, individual automaton. And then for a transition here, the transitions are labeled with a 0 or 1, that is a deadline hit or miss. So in the product automaton, the transitions are going to be labeled with 5 tuples, right? Binary strings of length 5, because if it is a 1 from this, there will be 1. If it is a 0 from here, it will be a 0, and so on and so forth. Now, once I have that product automaton, what I am, is there a question? Are you all with me?
It's okay. We can
Okay.
hear you, but there was some echo.
Maybe because somebody switched on a microphone or something at your end. Okay. So the question, so once I create this product automata, what we are asking is does there exist a accepting run in this product automata? That is there a sequence of transitions from an initial state to a final state such that in that run, every state transition is labeled by strings where there are at most two ones. Okay, now because why do I need at most two ones? Because in every slot, because in every period I am scheduling only two. So here it means that this transition means that in this period I will schedule only tasks T2 and T4, and T1, T3, and T5 are going to miss their deadlines. So if I can have an accepting run in this product automaton such that that accepting run has only transitions labeled with at most two ones, then it means that I have a feasible schedule. So, in other words, what we could do is that we have this resource constraint where in every step I can schedule at most two tasks. So, the first thing that I did was for each task, I identified what is its class of safe timing behaviors, and that class is represented as a regular language. And once I have these five regular languages, I construct their corresponding finite automaton, create a product, and from that product automaton, I can very effectively synthesize a schedule. So therefore, now we have a situation where tasks can miss their deadlines, and now I can run all of them on a much more resource constrained processor. But then I can still ensure that all the individual systems for whom I am considering these tasks, all of these systems are actually safe. Okay. So we will then have a schedule like this. So here you see that in the first period we are scheduling only these two tasks. In the second period we are scheduling only these two tasks, and so on and so forth. Now what is very interesting is that these schedules that we see cannot be specified by or obtained using any standard scheduling policy like EDF or first come first serve or fixed priority and so on. These schedules are very much dependent on the dynamics of the system and the resource constraints that you have, and they can only be derived if the system dynamics is appropriately modeled. Okay, so there we saw one example of what I outlined before, namely, even if an individual component is imperfect, that is, it doesn't always meet its deadline, I can still ensure that the overall system safety is guaranteed, and by exploiting this, I can design a system that is a lot more cost effective or uses less computational resources. Now I'll move on to another example. And in this example, we will show that if an autonomous system has, let's say, deep neural networks or machine learning components, even if those components are imperfect, that is, they make inference errors or inaccurate inferences, even then I can design a system where its system level behavior is guaranteed to be safe. Now, for that purpose, the setup that we have is that, again, we have a plant and we have different sensors, let's say cameras, lidars, etc. And the sensor data is fed into different neural networks, and these neural networks do a state estimation. So this X here is actually a vector. It has multiple state components. So the neural networks do state estimation, and using the state estimation, I am computing a control input and I'm then applying this control input. Now, of course, if the neural networks are not perfect, that then the state estimations are going to be also imperfect. And as a result, the behavior of the system is going to get impacted. So in many cases, especially, certainly in autonomous vehicles, often all of these neural networks corresponding to the different state components are implemented on a shared GPU. And, today, Many companies, including NVIDIA, they have what are called multi-instance GPUs. So which means that I have a single GPU, I can partition it into different parts and then concurrently run different neural networks. So in a setup like this, the question then is, how do I partition my GPU? I might not have enough GPU resources to put like the biggest neural networks for all of the state components. So I will have to make some compromise. So what do I do? If I have three neural networks, do I just partition my GPU equally among all the three and have same size neural networks for each of the three state components? Or do I give a bigger neural network to the first component for estimating the first component, and or a smaller one for the first, a bigger one for the second, and again a smaller one for the third? How should I partition my GPU? Or in other words, how should I partition size my deep neural networks? Now, the way we are going to do that is again following the concept of the system level safety. Now, the the reachable set of the system might be what we see here, like the deeply shaded part. But if the estimation for of each of the state components is uncertain, that is, I have a smaller neural network which is associated with higher inference uncertainty, then my estimate will be, some will also have this uncertain component, right? So this is the inner part is the actual reachable set. Then I estimate a reachable set that is bigger because of the uncertainty. And if there is even more uncertainty, my estimated reachable set will be even bigger. So the issue is that if I have an unsafe region, but I have neural networks that have a lot of inference uncertainty, I might say that my system is unsafe, but in reality, the system is not unsafe. In reality, the actual reachable state space is much smaller. It is because of the neural network uncertainty that I say that the system is unsafe. So, with that idea, what we will do is we will use the observation that the accuracy with which I need to estimate each state component is not going to be the same, right? There are some state components that have a much larger influence on the uncertainty in the overall system dynamics, or the uncertainty in the reachable state space of the system, whereas there are other state components whose uncertainty has a smaller impact. So the components that have a bigger impact, I would like to estimate those components more accurately. Whereas the components that have a smaller impact, I can estimate those components less accurately. Now, how do I do this estimation? So we need an efficient way of estimating which state components have to be estimated more accurately and which state components can be estimated less accurately. So what we will do is we will essentially measure the changes in the largest singular value of the system Jacobian when we are injecting uncertainty in each state estimate. Now, what is the system Jacobian? This is essentially the matrix of all the partial derivatives of the system dynamics. And why are we interested in the largest singular value? What we will essentially do is we will, sort the different singular values, and the largest one essentially tells me that that state component is inducing the most sensitivity. The one that is smaller than that is inducing less sensitivity, etc. And based on that ordering, we are going to partition the GPU, or we are going to size the neural networks. So I'll show you an example. So here, let's say that I have three state components. So one state component is estimating there is a vehicle, and the goal is that an autonomous vehicle always maintains its lane. And we have actually implemented this in what is called a F110 gym. This is a vehicle which is 1/10 the size of a F1 racing car. And there are three components. So one is one DNN, or deep neural network, is estimating the width of the lane. The width can vary. The other state component will estimate the lateral displacement, like within that lane, where exactly is the vehicle. And the third neural network from the LiDAR point cloud is estimating the vehicle orientation. So using this approach, it turns out that the width and the lateral displacement is a lot more important. It is more important to estimate them accurately than estimating the orientation accurately. So now we can have different kinds of DNN sizing strategies. So in the first strategy, I give a bigger neural network for the width estimation, and I have smaller neural networks for the other two. And similarly, in the second case, I have a bigger neural network for the lateral displacement estimation. And then the safety oblivious strategy is that I give a bigger neural network for the orientation, which is not so important to estimate accurately, and smaller neural networks here. And what we can see is that in each of these figures, we have the ideal trajectory, which is in blue, and then the actual trajectory is in red. So if I follow our strategy, you see that there is a much smaller distance between the blue and the red trajectories. Whereas if you use a safety oblivious DNN sizing, then you can see that the actual trajectory deviates a lot more from the ideal trajectory. And the ideal trajectory is the one where you have perfect inference, right? You sort of assign very big DNNs. Now, there are a lot of interesting observations we can make from here, right? And I'll talk about, let's say, only two of them. So the first is that the DNN sizing is actually more important than the overall GPU size. So even if I give you a very big GPU, if you do not do appropriate DNN sizing or appropriate partitioning, you might actually get very bad system level performance. And larger DNNs generally lead to bigger performance or better performance, but blindly using larger DNNs might actually degrade system performance, right? So if you have a very good or a very large DNN, but use it not judiciously, then your system might, rather than becoming safe, the system might actually become unsafe. So this is yet another example where using an imperfect ML component, you can actually still ensure system safety. I will skip this third example, and instead, I'll come to like the conclusion. So what I did was I kind of, gave you the blueprint of a design approach where, we are no longer trying to design perfect components, but rather we say that we will define some system level notion of safety and some tolerance in that space around the perfect behavior. And from that system level description of safety, we will try to derive component level imperfections. What are allowed imperfections in the components? And if you are able to derive them, then I gave you two examples where we say that, in terms of timing imperfectness, I can design a more efficient system. And then I could, in the second example, we saw that, I could have imperfect DNNs that make some inference errors, but by designing everything judiciously and taking into account the system level notion of safety, I could still do with a much smaller GPU size. Now, in the two examples, I use different notions of safety. If you sort of followed what I said, in the first case, we followed this notion of safety where I have a perfect behavior and I can allow some tolerance around that behavior. Whereas in the second case, my notion of safety was the size of the reachable set and the amount of uncertainty in the reachable set estimation. Now, there are many open research problems, like, for example, what would be a good notion of system safety, right? What is a safe behavior? What is an unsafe behavior? Answering that might be non-trivial and might need a lot of domain expertise. Once you have an understanding of that, how do you formally specify that system behavior? And then, once you have the system behavior, how do you then derive allowed component behaviors? And, once you have those component behaviors, can you then automatically synthesize schedules of the form that we did in the first example? In other cases, things might be more complex. And also, you could extend all of this beyond timing or machine learning that I spoke about, and go into domains like security, because again, you could say that it is not necessary to make the system perfectly secure, but I can compromise on the security. And if there is an attack, then it will deviate the system from its ideal trajectory, but it cannot deviate so much that it goes outside that safety pipe. And if we do that, then we might say that, well, then I don't need perfect protection, and I might do with less protection, and thereby I can reduce the cost, but still ensure that the specified system level safety property is satisfied. So with that, I will stop, and I'll be happy to take any questions. Thank you.
Pramodit, can you hear us?
Yes, I can hear you.
Okay, so we are sorry that this time we cannot serve fish fry, so that will remain due anyway. So
Right, right. Yes.
thank you very much for delivering a very interesting talk on, on the design of, what should I say, safe cyber physical systems, particularly in connection to autonomous vehicles. And you modeled, the modeling of the scheduling problem with automata theory and then DNA sizing. Very interesting talk indeed, Okay, so let me invite a couple of questions from the audience. Yes, please. Can you give the mic here? There is a question from the audience.
You won't be seen in the live telecast. You have to come up here. Can you make it quick? If you have any questions, come to the podium.
Or maybe you can take this,
Yeah, you can take the cordless mic if you want. But you have to.
Hello.
Would you please
Sir,
come up stage?
I have some basic questions. This imperfection which you were talking about, can it have some relation with the fuzziness? Or another thing is this timing you were talking, no? So there I was thinking about hard real-time system versus soft real-time system, because these are all basically to tackle into the imperfections. And the third point which I was thinking is, see, for example, if the diameter of your safety pipe is very small, say, for example, in nuclear power plant control, etc., then we cannot tolerate any imperfection. So
Yeah.
just your comments about this.
Yeah, absolutely. I think this is a very pertinent question. So to answer your first question about, how, what is the logic, what is the role of fuzzy logic in all of this? So here you would recall that what I try to do is I try to paint a very high level picture. And in that high level picture or plan, there are actually multiple components. So one component is what is your notion of system safety? And in the two examples I gave, I use two different notions of system safety. So one is where there is an ideal behavior and a safety pipe, and the other is where the size of the reachable set is a notion of safety. Now, there could be a lot of other notions of safety too, right? And, I unfortunately did not have enough time. I would have said a little bit more on, how to specify safety, what are other notions, how challenging is it to specify safety, and so on. So the how to specify safety is one actor in this drama, so to speak. And then the other thing is that once I have this notion of system safety, then how do I specify imperfection in the component? And there I also said that we used in the first example, we used a regular language to specify imperfection, which is patterns of deadline hits and misses. Now one could probably, I mean, I am no expert in fuzzy logic, but one could, for example, have other possible uh, descriptions of component behavior. And there I kind of see that, maybe it could be a fuzzy logic description of component behavior, and different notions of that specification or different specifications will essentially capture different types of imperfections that can be allowed in the component. Now, in terms of hard real-time systems and soft real-time systems, I think we are not quite dealing with either hard or soft. In fact, we are dealing with a different notion, because we are allowing deadline misses, and soft real-time systems actually do allow deadline misses. But the type of deadline misses we allow have to fall within some specification. We cannot allow arbitrary deadline misses. So in that sense, it is, you could call it a hard real-time system, because there are certain deadline misses we can allow, or certain classes of deadline misses we can allow, but certain others we cannot allow. But it is also similar to soft real time, because we do allow some deadline misses. But in the traditional soft real time systems, there is no specification that the system has to follow, right? It just says that it can occasionally miss deadlines. So I would say that our notion of deadline misses is some sort of a hybrid of a soft and hard deadline misses. And coming to your last question of if the safety pipe is too small, yes. If the safety pipe is wider, you will get more savings. If the safety pipe is more narrow, you will get less savings. Now, how much savings you will get corresponding to a safety pipe depends totally on the dynamics of the system, right? So, for certain systems, even with a very narrow but with a non-zero diameter, you might get lots of savings. There could be other sorts of dynamics where even with a very, very big safety pipe, you might not get enough savings. So it totally is system specific.
Yeah, thank you. Any other questions? Okay, Samarjit, I have just a comment,
Yes.
So you talked about designing, safe and perfect system with imperfect components, right?
Yes. Yes.
75 years ago, John von Neumann gave a celebrated lecture, designing reliable machines using unreliable components.
Yes.
Some connection with that, right?
Absolutely. So there has been a lot of work on having in the context of hardware design, having processors that are kind of subject to aging, subject to soft errors and whatnot. And as, let's say, device geometries are becoming smaller, these kinds of errors or imperfections at the component level are unavoidable. So the question is, can we take this unsafe or unreliable components and still build a safe system? Here we are doing exactly the same, but at a different level of abstraction. So here we are not talking about hardware components, but we are talking about a bigger, let's say, an autonomous system that has subsystems like machine learning, scheduling, sensor fusion, sensor processing, whatnot. And the question we are asking is, can we make these bigger components imperfect, but still design a system that is safe, and in the process, make the system more cost effective, let's say.
Samarjit, thank you very much for your wonderful presentation. Any question? Okay, one more.
Actually, not a question to Samarjit, but it's a comment on what Bhargavda said. So I heard that von Neumann actually generated a very interesting puzzle. So how to design a unbiased experiment with a biased coin. It's actually an exercise for students, okay, but it is very much related to that. So it's all starts from there. Design an unbiased experiment with a biased coin, because all practical coins are biased, right? And Samarjit, thank you for giving the lecture again this year. Next year we will try to have you here. Okay.
Yes, I mean, next year actually I will not teach in the fall semester. So from May till December I am available to travel. But again, next year in January I will have to teach. So I think if you organize your conference at the end of December, it might be useful for lots of people coming from the US or maybe even Europe.
And we are a institute which adapts a lot. Always adapts with students' absence and all everything. So we'll adapt with you also. Okay. We'll try also. Okay.
Thank you very much. Thank you.
Once again, and let us give a big hand to Samarjit.
Thank you.
Thank
So
you,
I-
Professor Shomoji Chakraborty, for your insightful and enlightening talk. Thank you, Professor Bhargav B. Bhattacharya, for chairing the session. I would like to request Professor Proshenjit Gupta, sir, to kindly felicitate Professor Bhattacharya.
Felicitate Professor Samarjit Chakraborty.
Unfortunately, it's online, so we convey our felicitations to him
Thank you. Thank
on
you.
the internet. Huh. Can we have a big round of applause, please? Fine. We will now take a short tea and coffee break. We shall return here at 10:45 to continue with the proceedings on track B. So I would request you all to please go to the executive hall. We'll see you back. Thank you. Yes, I will. Yes, thank you, Shomurjit Chakraborty sir, once again. Thank you, sir.